This is part 2 of lecture 16. In part 1, we discussed about the basic working principle of oscillator circuits, and we discussed the necessary conditions for the positive feedback amplifier to work as an oscillator, to have sustained oscillations. So in this part, we'll see some circuit example of oscillator circuits, the different situations that we have discussed, the conditions, how we apply those conditions to get the oscillator circuits. Basically, we discussed about the two situations, one with the positive gain amplifier, the other with the negative gain amplifier. And in this part, we will see the circuit example for each of these situations, how we can obtain an oscillator circuit with positive gain amplifier, and how we can get an oscillator circuit using a negative gain amplifier. So first we see a circuit example of oscillator circuit using a positive gain amplifier, which is also known as the Wien bridge oscillator. This is the circuit that uses a positive gain amplifier to obtain the oscillator circuit. As you can see, the op amp here basically connected in non-inverting amplifier configuration with the resistors R1 and R2, R1 being grounded, and in the negative feedback path, in the positive feedback path, we have this RC, this series, and then RC in parallel connected. So this goes into the positive input terminal of the amplifier, so that makes it a positive feedback amplifier. So this is the basic amplifier of this oscillator circuit, which is a non-inverting one with positive gain, and below that, this RC circuit, it makes the frequency selective feedback network. So it samples the output voltage and produces a feedback voltage that is applied to this non-inverting input terminal, and that is amplified by this non-inverting amplifier. So in this case, the basic amplifier, which has a positive gain, so there is no phase shift from input to the output. We can say 0 degree phase shift or 360 degree phase shift through the basic amplifier, and so the feedback network should also provide 0 degree or 360 degree phase shift, and the total phase shift will remain 0 or 360 degree. Now we'll analyze this Wien bridge oscillator circuit to determine the conditions that we must fulfill in order for the circuit to work as an oscillator circuit, and also we'll determine the expression for the frequency of oscillation. The starting point for this is the loop gain. We know that for the oscillator circuit to work as an oscillator circuit, it must satisfy the loop gain conditions, that the magnitude of the loop gain should be 1 and the phase angle should be 0. So first we start with the gain of the basic amplifier A. The gain of this amplifier defined by output divided by input. In this case, input voltage is the voltage that appears at the non-inverting terminal, that is Vf in this case. So gain of the basic amplifier V naught by Vf, and since this is a non-inverting amplifier and the gain expression is our well known, this 1 plus R2 by R1. So that is the gain of the basic amplifier, and now we need to determine the feedback factor beta for the feedback network. The feedback factor is defined as the output the voltage of the feedback network, that is Vf, divided by the input voltage to the feedback network, that is V naught. So Vf by V naught is the feedback factor for this feedback network, and we need to analyze this RC circuit to determine the feedback factor. Now the RC circuit here just works like a voltage divider. You can see that R and C, this R and C, these two are in series, connected with the output node and the inverting input terminal, and then at the inverting input terminal we have the R and C in parallel. So we can denote these two RC in parallel, the parallel combination, as ZP, the impedance of these two parallel combination, and RC, these two in series, so the impedance of the series combination at ZS. And then we can apply the voltage division rule for Vf by V naught is Zp divided by Zp plus Zs. So that is our feedback factor for the frequency selective feedback network. Now multiplying these two, we get the loop gain for this oscillator circuit. So the first term here is the gain of the basic amplifier, and the second term is the feedback factor beta, which we can simplify like this, dividing both the numerator and the denominator by Zp. So this we simplify like this, and further we can express like this. So this is our expression for the loop gain, and that loop gain should be 1, the magnitude should be, and phase angle should be 0. Now here in this expression we have the ZS is the series combination, and we have Zp, which is 1 over Zp actually, and 1 over Zp is the, we know this is, we call it admittance, and admittance of this here we have the two parallel branches R and C. So in this case the admittance of the parallel branch is equal to the summation of admittance of the individual branches. So we have the admittance for R, which is 1 over R, and that plus the admittance of this reactance C, which is just j omega C. So that will be our 1 over Zp, or the admittance of this parallel branch. Now we can do some simplification of this loop gain expression, replacing Zs by R plus the series combination, and 1 over Zp, the admittance of this parallel combination. Now further manipulation of this will give us this. If you multiply this out, R and 1 over R makes it 1, then you multiply these two, you get 1 over j omega C R, then multiplying j omega C by R you get j omega C R, and multiplying these two you just get 1. So that we just simplify and we can express like this. So this is our final expression for the loop gain of this Wien bridge oscillator circuit. We now impose the condition for sustained oscillation, 1000 criterion, on this loop gain expression. The criterion states that both the magnitude states that the magnitude of the loop gain should be 1 and its phase angle should be 0, which we can also express like this, that the real part of the loop gain should be 1, magnitude is 1, the imaginary part of the loop gain should be 0. That means the phase angle, for the phase angle to be 0, it cannot have any complex part. The complex part should be 0, only then phase angle will be 0. So this is how we can also express the condition for the Barkhausen conditions for sustained oscillation. So first you can equate this. This is the imaginary part of the loop gain, and this has to be 0 if the phase angle has to be 0. So if you equate that and see that this, we have the frequency term, we have R and C. So these circuit component values and the frequency, they together will determine the frequency. You see R and C, if you assume them to be fixed, then for different frequency, now you can have different value for this, and there will be one particular frequency for that this part will be, this complex part will be 0. Let's say our frequency is omega naught, and this frequency omega naught, this part becomes 0. So if you do for the simplification of this expression, multiplying both sides with j omega naught CR, we can write this like this. Now we have j omega j squared here. J squared is -1, so replacing that for -1 expressed like this, and then we can write like this, and that after simplification omega naught CR is 1, so it means omega naught the frequency. Finally we get this expression for the frequency of oscillation. So this will be the frequency for which the imaginary part will go to 0 and phase angle will be, so that the phase angle or phase shift will be 0. So if the signal frequency is this or there, so that is the frequency for which the total phase shift around the loop will be 0, and that is the frequency of oscillation. That means the output signal, this for which the frequency for which you will have the sustained oscillation at the output is this frequency. This is an angular frequency, radian per second, and we can express it in hertz, regular frequency f0 1/2 by CR. So that will be our frequency of oscillation. So the circuit component values, the R and C, will determine at what frequency the circuit will oscillate, or what will be the frequency of the output signal. So you see that you can easily fix the frequency of the output signal by fixing the values of R and C. If you vary the value of R or C, you can also vary the frequency of oscillation, and that is why this is also called the frequency selective feedback network. This is the network that we can use to fix the frequency of oscillation. So now we go back to our loop gain expression again, and we impose the other condition for the oscillation, that is the magnitude of the loop gain should be 1. That's here it is written as a real part of the loop gain should be 1, while the imaginary part should be 0. So now you have to take the real part of this expression for the loop gain. The real part, we get the real part when you remove this imaginary part, or you put the 0 for the imaginary part. So this imaginary part will be 0 for the real part. So we just put 0 here, and then we get the real part, and real part has to be the magnitude of this real part should be 1, and so that simplifies to this 1 plus R2 by R1 divided by 3, because the imaginary part is set 0, and that has to be 1. And this will give us the value for the gain of the amplifier. 1 plus R2 by R1 is the gain of the basic amplifier, so that should be 3. So in order to have a magnitude of 1 for the loop gain, the basic amplifier should have a gain of 3. So that is another deduction that we get from this analysis. This also we can express as the ratio R2 by R1 should be 2. So if we satisfy this condition that the ratio R2 by R1 is 2, or the gain of this forward gain of the basic amplifier is 3, then we will have a sustained oscillation at the frequency of 1 over 2 pi RC. So that completes our analysis of the Wien-Bridge oscillator circuit. We have determined the conditions needed to get the sustained oscillation at the output, and also we have determined the frequency at which we will get the signal, or at which the circuit will oscillate. So next we'll discuss another circuit example of the oscillator circuits that is based on the negative gain amplifier. The Wien-Bridge oscillator circuit was based on the positive gain amplifier. In this case, now we see an example that is based on the negative gain amplifier. So this is also known as the RC phase shift oscillator, and this is the circuit where we use an inverting amplifier as our basic amplifier. You can also use a common emitter amplifier, because that also has a negative gain. And then feedback network, we have as the feedback network, we have this combination of R and C's, and this feedback network, since we have a negative gain amplifier, that will give you 180-degree phase shift from input to output, and then you have this RC, the circuit that should give you another 180-degree phase shift, so that the total phase shift is 360-degree when the signal completes one complete loop. You see that the feedback network, the input is coming from the output, and the output of the feedback network, which is the voltage here indicated as VF, the feedback voltage, goes into the input of the basic amplifier, that's our inverting amplifier. Now you see that RC circuit, we have here three parts of this RC circuit, three segments. Each of the segment will give you a phase shift. The RC circuit can provide a phase shift of less than 90-degree. It can't provide 90, to be always less than 90-degree, and we need total phase shift of 180-degree through this feedback network. Since we need total phase shift of 180-degree, so we'll need at least two segments of this RC, at least three segments of this RC circuit to get a phase shift of 180-degree, since each one can provide a maximum which will be always less than 90. So if you design each of these segments so that they can provide 60-degree phase shift each, so the three segment RC circuit segments together, they will provide a phase shift of 180-degree. So that is the basic idea, and that is why this feedback network is also called the RC phase shift oscillator. Each of the circuit, they are providing a shifting in the phase by 60-degree to the signal, and thus providing the necessary 180-degree phase shift from input to the output of this feedback network. So the conditions that we need to fulfill for the circuit to work as an oscillator circuit or to have a sustained oscillation, and the procedure is the same as we have seen it as we have shown it for the Wien-Bridge oscillator. You start with the loop gain expression for the loop gain, determine the expression for the loop gain, get the product of the gain of the basic amplifier A and the feedback factor beta. So you see that the gain of the basic amplifier A is nothing but minus RF by R, And then the feedback factor, this is not that simple circuit. I mean, there are 2-3 nodes here, so you need to do some nodal analysis here, assign some node voltages to these two nodes and do the analysis, and through the nodal analysis you can determine the ratio of VA by V naught, that is the feedback factor for this feedback network. And then you take the product A beta, equate it to 1 0, equate the real part to 1, the imaginary part to 0, and from that you will get the frequency of oscillation and also the magnitude of oscillation. So these are the conditions that you impose on the loop gain, as we have done for the Wien bridge oscillator. First start with the imaginary part, equating the imaginary part to 0, and that will give you the frequency of oscillation. And in this case, the frequency of oscillation that we will get will be this. So slightly different. You have here square root of 6 and the additional factor here for the frequency of oscillation, and the gain of the basic amplifier in this case, by imposing this condition that magnitude of the real part should be 1, that will give you the gain of the basic amplifier, and that will be 29. So that is so you have to set the gain of the basic amplifier as 29. Then you will get a sustained oscillation at the output with this frequency. And like before for the Wien bridge oscillator, you can also fix the frequency at your desired level by fixing the value of R or C.